Ida that my name is Atina Ahdika, and you can call me Atina. And today I will give a lecture regarding the introduction to basic probability. So I will share my slides.
Sure.
Okay. Yeah. Can you see my slides, Dr. Ida?
Yeah, clear.
Yeah. Okay. Okay, so everyone, today we will discuss some materials about the introduction to basic probability, and this is the outline of our discussion today. So first, I will give you some basic concept of the set theory, and then the concept of the probability and counting rules, and then I have some exercises for you through the quizzes, so you can prepare your smartphone. Okay, but because we just have 2 hours, so yeah, I hope that the time will be enough for all of these materials. But I think we just go with whatever we can have today. Okay, so first, for the set theory, I will give you some explanation about some termination in statistics in the set theory. First is about the experiment, and then sample space and event. I don't know whether you have or you get these materials in the class, but I think it is important for all of the statisticians to know what are experiment, and then sample space and event. Okay, for the first one, experiment. What is the experiment? Experiment is a process, so we will focus on a process that when it is performed, it will produce some random possible outcomes. For example, for the simplest example, we know when you play tossing a coin, right? So you know that the outcomes will be head or tail, and we cannot control the outcomes of the experiment. So when we toss a coin, we cannot control that. I want that that will be appear is head. We cannot control that. So it is the concept of random. Yeah. So the experiment is a process. When it performed, then it will produce random possible outcomes. Okay. So for the second is about the sample space. If in the experiment we have a process, so the sample space is set or collection of all outcomes for an experiment, and it is usually denoted by S. Yeah, so if we toss a coin, and then the sample space will be head or tail, and we usually write it as, okay, how Dr. Ida, I'm sorry, how could I write in this slide? I'm not used to using.
Can you sketch it? Sketch on your slide.
Sorry.
If you were able to
Give me a
on
minute.
your slide.
Yeah, give
Sure,
me a
sure.
minute. Yeah.
Sure.
I have. I will look for the button to annotate the slides. Oh, there's no button to annotate the slide. I use the other application here using Wacom. So how
So
can I?
you should be able to sketch on your PowerPoint slide using your Wacom, because because I'm also using some Wacom tablet.
Yeah, I use Wacom.
So you can sketch from on your slide straight. Can you try it? Can you?
I cannot do this. I can't do this.
Okay.
Maybe okay. I'm sorry, Dr. Ida. I will join with another application. I will use my iPad so I can,
Okay, sure.
yeah,
Sure,
I
sure.
can
We'll
stretch directly. I'm sorry for this one.
no problem, no problem.
Ah, I'm sorry, Dr. Ida. Give me a minute.
Sure, sure, sure.
It's problem. I'm sorry, Dr. Ida. My WhatsApp is still on loading. I will join with my other device. Okay, Dr. Afida. Okay, while we wait for the other device, I will still continue my presentation first.
Okay.
Yeah, I'm sorry once again, Dr. Ida. Okay, can you see my slides?
Yeah, clear.
Yeah. Okay, so we have sample space. Yeah. Okay. Sorry, Dr. Ida, I joined the meeting with my other device. Please allow my device. Okay, so I will share. I'm sorry, I will share from my iPad. Share. Okay. Yeah. Okay, is it clear?
Okay, clear.
Okay, so I will continue my explanation about the sample space. So back to the definition of the experiment, we will use the simplest example. Imagine that we toss a coin. Yeah, so this is the process. The process of tossing a coin. This is the experiment. So we will have a sample space, which is the collection of all outcomes for this experiment. So we always, or we can write our sample space as head and tail, something like that. So you can see the difference between experiment and sample space. Experiment is the process that produce random possible outcomes, and the sample space is the set or the collection of all outcomes of the experiment. Let me give you another example. When we toss a die with six die, six number, 1, 2, 3 until 6, then the sample space will be 1, 2, 3, 4, 5, and 6. So this is how we write the sample space of our experiment. Okay, and the third one is about the event. Event is a collection of one or more of outcomes of an experiment. So we can also say that event is the subset of the sample. So for the tossing a die, imagine that I can define an event. Let's call it as A. The event that the outcomes of the tossing a die is even number. So we can calculate, or we can write the outcomes of the event A as 1, 3, and 5, like that. So A will be the subset of S. Then A is called event. Okay, so I will give you another example. Here is the other example of experiment, sample space, and events. So first, what I say before, that we can toss a coin. So the process of tossing a coin once is the experiment. And the sample space of this tossing a coin process is head and tail. So we can just write the element or the outcomes of this process. And then we can also define the event. Yeah, just like maybe appear head from once tossing a coin. So we can write the event as A is consists of H, or consists of head. And then the other example of the experiment is rolling a die once. Like I said before, we have the sample space of 1, 2, 3, 4, 5, and 6. And then we can also define an event that is a subset of the sample space to be the even number or the odd number. Yeah, so the P here is the subset of the sample space S here. Okay, another example is when we toss a coin twice. So from the tossing twice from a coin, we will have the outcomes like head, and then head and tail, and then tail and head, and tail and tail. So we can write our sample space like this one. And then we can also define an event that represents that the outcomes of the tossing a coin twice, that we have at least one head. So the C here is the collection of the subset of the sample space, which consists of the outcomes with at least one head. Okay, so that is the examples of the sample space and then experiment and then the event. Wait, why the screen is paused? Is my screen okay in your, is my slides okay in your screen?
Okay.
Yeah.
No problem.
No problem. Okay. So the other example is play lottery. The outcomes of a play lottery, when we play a lottery, is we can win or we can lose. Then the sample space, we can write it as win and lose. Or the other example of the experiment is select a worker. So when we have a company and then I will select gender of a worker. So we have male and female worker. So this is the examples of the experiment, sample space and events. Okay, I will continue to the next explanation about the properties of events. We have some properties of events. The first one is union of events. So if we have any two events, let's say it as A and B from a sample space S, then we can define a new event that we can write it as like this, A cup B. So the notation like U is the union of event. So we can say that A union of A and B. So what is the union of A and B? Union of A and B consists of all outcomes that are either in A or in B or in both of A and B. So if we take any outcomes from A union B, let's say I will take any outcomes, say A, little a. So this little a can be in A or in B or in both A and B. So we call it as union. Okay, for example, imagine that we toss a die. So we have the sample space of 1, 2, 3, 4, 5, and 6. And then I have an event A that is that the die appear at least 3. So we have A here is 3, 4, 5, and 6. And then I define another event. I say B, and B is the set of all the odds number of tossing a die. So we have here 1, 3, and 5. So the union of A and B is that we combine or we unify all of the outcomes in A and B. So the union of A and B will be 1, 3, 4, 5, and 6. We will write the same outcome once. So like this, we have 3 here in A and 3 in B. And then we have 5 in A and in B. But we just have to write it once in our union events. Okay, so this is the example of union. Okay, and then I will continue to the next slide. Okay, for the second properties of the events, we have intersection of events. So for any two events, A and B of the sample space S, we can define the intersection of events or denote by cap like this. We call this symbol as cap, yeah, and this is the intersection of event. Then the intersection of event consists of all outcomes which are both in A and B. So if we see the Venn diagram here, we have event A and we have event B. So the intersection is every outcome which is in A and in B. So we can say if I take any outcomes A, little a, so little a will be in this shadow graph. So A must be in, the little a must be in event A, and it is also must be in event B. So this is the intersection of events. Okay, and then the third property is the mutually exclusive event. So if we have two events, A and B, and there is no intersection between A and B, then we can say that A and B are mutually exclusive. So like this one, if we have intersection, then the diagram of A and B will be like this, A and B. This is when we have intersection. But if we have no intersection or we can say that the intersection of A and B is empty set. This is the symbol of empty set. So we can say that A and B are mutually exclusive. The example of the mutually exclusive events are that we have one die, tossing a die once, and then like before we have sample space of 1, 2, 3, 4, 5, and 6, and then I have A as the odd numbers, so I have 1, 3, and 5, and then I have B that is even number, so I have 2, 4, and 6. Then there is no intersection between A and B. So we can say that A and B are mutually exclusive. Okay, and then uh, the next property is complement of event. Okay, so the complement of event is that we have a set that the outcomes of the set A is not in the other event. Or for simplicity, that we if we have event A, then we can define AC, AC, or A apostrophe, yeah, which means that it is the complement of A. So the AC or complement of A will occur if only if A does not occur. So if I take any little a, which is element of A complement, then A will not be in A. Yeah. So if we describe it in the Venn diagram, we can took A, little a, outside the A here. So this is the complement of event. For example, still with tossing a die, we have sample space of 1, 2, 3, 4, 5, and 6. And then if, suppose that I define an event A, which is the number of less than 4, then we have 1, 2, and 3 here. So the complement of A is 4, 5, and 6. Yeah. So complement of A occur if and only if A does not occur. Or we can say that we take any element of A complement, so this little a will not be in A. Okay, and the last property of the events is partitions of sample space. Yeah, you can see the description here. Imagine that we have sample space of S, and then we have a set of events, call it as A1, A2, A3, etc. And then the set of events is said to be partition of sample space S if um, there are two properties that the set of events have to require. The first property is all of the events are mutually exclusive. So there is no intersection between A1 and A2 and then A1 and A3, A2 and A4, and all of these events will have no intersection. Or we can say that all events are mutually exclusive. And the second property is that the union of all AE will be formed S, or will be formed sample space. So we can say that A1, A2, A3, and extra are the partitions of the sample space S. Okay, so this is the example. Oh, sorry. The example for partitions is like this. We still will use the tossing a die once. So we have sample space of 1, 2, 3, 4, 5, and 6. And then consider that I have A1, which consists of 1, 2, and 3. And then A2 consists of 4. And A3 consists of 5 and 6. So A1, A2, and A3 are the partitions of sample space because there is no intersection between A1 and A2, between A2 and A3, and between A1 and A3. And then the union of A1, A2, and A3 form a sample space. Okay, I will give you another example here. Consider that I have event of B1 consists of 1, 3, 5, and then B2 consists of 2 and 3, and then B3 consists of 4 and 6. So are B1, B2, and B3 partitions of sample space? Are they the partitions of sample space? Can I ask one of you? So we have interactive discussion. Dr. Ida, can I just call one of the students to answer?
Oh, sure. You can ask anyone. Yeah.
Okay. So I will call Miss Aida Patricia. Miss Aida, can you answer my question? Hello? Hello, Miss Aida, can you answer my question? I have B1 consists of 1, 3, and 5. And then I have B2 consists of 2 and 3, and B3 consists of 4 and 6. And the question is, are they partitions of sample space? Let me call another student. Okay, how about Adlin Sofia? Hello? Is it Miss or Mister?
Batrisha.
Dr. Ida, is my voice clear? Hello, Dr. Ida? Is my voice clear? I think I have unstable internet maybe, but I think it's okay here.
Problem with my internet.
Yeah?
Okay. Okay then. No, it's okay now. I have problem with my internet.
Okay. Okay. So whose internet is unstable here? I don't know.
Maybe we can ask the other student.
Okay. Yeah, I will call another student. Ahmad Hamizan. Do you get my question? Or maybe because it is holiday, Dr. Ida. So
Yeah.
Yes, madam.
Okay, Mr. Ahmad. Yeah.
Yes.
Do you get my question? We toss a
Uh,
die, yeah, and then we have sample space of 1, 2, 3, 4, 5, and 6, and then I have three events consist of B1, B2, and B3 here, like this. So my question is,
okay.
are they the partitions of the sample space?
Yes.
Yes. How come?
Wait. My line is a bit slow here.
Yes. Sorry.
My internet a little bit slow.
Oh,
Try to
okay.
answer the question.
Okay, so we can call any set of events as the partition of sample space if the set of events fulfill two requirements. The first requirement is all of these events are mutually exclusive, or we can say that there is no intersection between all of the events. And the second requirement is that the union of all of these events will form sample space. So if I have an experiment of tossing a die once, which we have the sample space of 1, 2, 3, 4, 5, and 6, and then I have these three events, B1, which consists of 1, 3, and 5, and then we have B2, consists of 2 and 3, and we have B3, consists of 4 and 6. So are all of these B1, B2, and B3 the partitions of sample space? So your answer is yes.
Yes, correct, madam.
Okay, so let's see. Are they fulfill these two requirements? We will see. For the first requirement, we have to prove that all of these events are mutually exclusive. So we have to prove that between B1 and B2, and between B2 and B3, and between B1 and B3 will have no intersection. And we can see here that B1 and B2, are they have intersection? What is the intersection between B1 and B2? Still with Mr. Adam? Sorry, Mr. Ahmad. I'm sorry. Yeah, so what is the intersection between B1 and B2? We have B1 consists of 1, 3, and 5, and then B2 consists of 2 and 3. So what is the intersection between B1 and B2? Okay, I will call another student. Aidil Iqbal. Are you there?
Yes, madam.
Yes, okay. So what is the intersection between B1 and B2?
3.
3, okay. So there is intersection between two events. So can we say that B1, B2, and B3, the partitions of the sample space? Still with Aidil Iqbal?
I think it's no.
No, yeah. So the answer is no because the first requirement is not fulfilled by these three events. Yeah, although the second requirement is fulfilled, yeah, we can see that the union between B1 and B2 and then B3 form sample space that is 1, 2, 3, 4, 5, and 6. However, we can find that there is intersection between B1 and B2. So the first requirement is not fulfilled by the set of events. So that we cannot say that this is the partitions of the sample space. Okay, thank you, Ahmad Hamizan and Aidil Iqbal. I will continue to my slides then. So this is the other example for all of my explanation before. Consider that there is an experiment of tossing a coin 3 times. So we will toss a coin 3 times. So we have the sample space of 3 head, and then head, head, and tail, and then head, head, tail, and head, tail, 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 head, tail, 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 head, and tail, tail, tail. So we have 8 outcomes here. Then let A be the event that at least 2 tail appear. So we have the element of the A here, head, tail, 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 head, tail, 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 head, and tail, tail, tail. And then we have P, that is the event that 1 head appears. So we have the element of P here, head, tail, 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 head, tail, and tail, tail, head. So my question is, the first question is, what is the union between A and B? Okay, I will call Izzati Suhaimi. Are you there, Izzati? Or maybe Iwana, because you open your mic.
The mic.
Yeah. I think you're ready to answer.
Yeah.
Yeah, it's still simple. Please,
Iwana?
Iwana, yeah, can you answer my question? What is the union between A and B? Okay, then disappear. Okay, another one, maybe Nur Afika. Nur Afika, are you there? Or anyone? Yeah, I think anyone can answer this question. please open your mic and just answer. Anyone? So what is the union between A and B?
Anyone? Anyone with the answer?
Of AB.
Yeah, sorry. Who are saying here? Please say
Hello?
your name. Yeah, yeah, hello. You can say your name and then answer my question.
Sorry, ma'am, but can you repeat the question?
Oh, okay. So we have an experiment of tossing a coin 3 times. That we have the sample space like this. This one is the sample space of our experiment. And then there are 2 events like this. Event A and B, which consists of this is the element of A and this is the element of B. And my question is, what is the union between A and B?
Union, is it
Yeah.
every element?
Every element, okay. Then
I mean, is it all elements?
how can we write the element here?
Yes, ma'am.
Just say, yeah, just say it. What is the element of the A union B?
HTT,
Okay, HTT,
THT,
THT,
TTH.
okay, TTH.
That's it.
That's it. Okay.
Yes, ma'am.
Are you sure? This
How
is
about
Is
just
it
TTT?
because it's same element, right?
yeah. The same element is for the intersection, but this is the question is union.
Union.
Yeah, the question is union. So if union, so we have to write all of the outcomes, but in A and in B.
Oh, yeah,
So
TTH.
yeah,
TTT.
so we have to add TTT here. Okay, sorry. Okay, so we have also the additional TTT here. Okay, thank you, Afif. Yeah, Afif Fahmi.
Yes,
Okay, thank you for your answer. And then my second question is, what is the intersection between A and B? Anyone can answer?
sorry, what was it?
Yeah, still with Afif. You can answer the question. What is the intersection of A and B?
Intersection.
Sorry?
Is it intersection?
Yeah, yeah, intersection.
HTT,
HTT, okay.
THT,
THT,
and TTH.
yeah, and TTH, okay.
Because
Yeah,
both same element.
yeah, correct. So for the intersection, we have to write all of the similar element but in A and B. Okay, thank you, Afif. And then my next question is, what is the complement of B? Anyone can answer my question?
Not from B, yeah.
You can answer, or the other student can also answer. But if you want to answer, I think it's okay. It's good, Afif. You will answer?
I want
Yeah.
is it TTT because it's the different element.
Okay. TTT. Okay, I will ask you once again. Are you sure with your answer? That the complement of B is only TTT? Yeah, so the complement of an event is all the outcomes from the sample space which is not in B. So you have to compare it with the sample space, not with A, but with the sample space. So the other element which is not consist in B from the sample space of S is the complement of the B. So the complement of the B will be HHH, HHT, HTH, and then THH, and the last one is TTT. Okay, so for the complement of an event is all the outcomes that is not in those event, but they are on sample space. So not just only compare with A, but you have to compare with the sample space. Can you get it? Or I will ask Afif, maybe can you get it with this third question?
Yes, ma'am.
Yeah, okay. Okay, thank you, Afif. And then I will continue to my explanation. Oh, okay, sorry. But before I continue to our discussion today, I will give you time to ask any question. Please, Dr. Ida, if anyone have any question, they can raise their hand and ask to me.
Okay. Okay, thank you. Do you have any question? Anyone?
No, madam.
Okay.
No, not yet. Okay.
Not yet.
Yeah. Okay, so I will continue to the second section of our class today. It is about the concept of the probability. So we will discuss about the probabilities which is defined on events. Yeah. Okay, so first consider an experiment whose sample space is S, and then we have event A of the sample space S, and assume that a number of PA, or the probability of the event A, which we can calculate it as the proportion between the number of outcomes in A and the number of outcomes in sample space. And then the probability of A have to satisfy these following three conditions. The first condition is that the value of PA, or the probability of A, is between 0 and 1. So the value of the probability will not be less than 0 and will not be greater than 1. And then, oh, I'm sorry, I think I have a typo here. So the second condition is that the probability of S, so this is not A but S, the probability of the sample space is equal to 1. And then for any sequence of events A1, A2, etc. that are mutually exclusive, so reminder that mutually exclusive is when we have no intersection between events. So the probability of the union of all AE will be the summation of the probability of all AI. So if we have A1, A2, and A2 and A3, which are mutually exclusive, then the probability of the union between A1, A2, and A3 will be the sum of the probability of A1 plus A2, probability of A2, plus probability of A3. Yeah, but this is only for the mutual exclusive event. Okay, and then this is the example. Suppose that in a group of 500 women, 120 have played golf at least once. And then suppose that one of these 500 women is randomly selected. So I select one of these 500 women randomly. So the question is, what is the probability that she has played golf at least once? Yeah, so the solution is, because the selection is to be made randomly, so I cannot know what I select. So each of these 500 women has the same probability of being selected. Thus, we have the probability that the one female, one women that is selected is 120 over 5. We will select one person that played golf at least once. Okay, so I think it is simple because I think you all have learned it in senior high school. And then this is the other example. Suppose that a head contains 40 marbles. Of them, 18 are red and 22 are green. And then we will select one marble randomly without any understanding about what is the color of the selected marble. And then the question is, what is the probability that those marble is red? And the second question is, what is the probability that those selected marble is green? So I want you to answer. Please, maybe Nur Amalina binti Zulkifli. Nur Amalina, can you answer my question? What is the probability that the selected marble is red? Yeah, please answer. Yeah. What is the probability that the selected marble is red? The probability of red? How do you calculate this?
Nur Amalina Zulkifli.
Yeah.
Sorry.
18 divided by 40.
Okay, 18 over 40, right. Okay, thank you, Nur Amalina. And then what is the probability that the selected marble is green? Can anyone answer it? I think it is quite easy. You can answer. Nur Tasnim, can you answer my question? Nur Tasnim Husna.
Nur Tasnim.
Yeah, or anyone, just answer my question. It is quite easy, I think.
22 over 14.
Yeah, 22 over 40. Okay, thank you. Okay, so that is how we calculate the probability, the basic probability. Okay, and then I will jump to the next discussion, that is about the additional rules of probability. So we have the theorem here. We have two rules for the additional rules of probability. So this is the first one is for the simple case. So if we have two events, A and B, that are mutually exclusive. Reminder, we have to remind that A and B are said to be mutually exclusive if there is no intersection between A and B. Yeah, so if A and B are mutually exclusive, or in other words, we can say that there is no intersection between A and B, then the probability of the union between A and B will be the summation of probability of A and probability of B. Okay, let's see the example. When we toss a die once, we have the sample space of 1, 2, 3, 4, 5, and 6. And then suppose that we have even A, which consists of 1, 2, and 3. And then we have even B, which consists of 4, 5, and 6. Then the probability of the union between A and B, we can see that there is no intersection between A and B. Yeah, there's no similar outcomes in A and in B. So the probability of of the union between A and B is the summation between probability of A and probability of B. So what is the probability of A? If we have three outcomes like this here, what is the probability of A?
3/6.
Okay, 3/6. And then what is the probability of B here?
3/6.
Okay, 3/6 also. So the probability of the union between A and B is 3/6 plus 3/6, or it is equal to 1. Yeah, I will give you another example. I have C here. So C consists of 5 and 6. So what is the probability of the union between A and C? We have to calculate the probability of A and the probability of C. For probability of A, we have 3/6. And what is the probability of C here? Anyone?
2/6.
Okay, 2/6. Okay, so what is the probability of the union between A and C? We will sum the probability of A and probability of C. 3/6 plus 2/6. So we have 5/6. Okay, I think it's quite easy. We can continue to the next discussion. So then we have the general case for the additional rule of probability. We have the question number 6 here for the general case of the the additional rule of the probability. So if we have two events, A and B, then the probability of the union between A and B will be equal to the summation of the probability of A plus probability of B minus the probability of the intersection between A and B. So if there is no intersection between A and B, or we can say that A and B are mutually exclusive, then the probability of the intersection between A and B will be 0, and then this general case will be the simple case. Okay, so I have the other example here. Suppose that we have an experiment which tossing a coin 3 times. So we have the sample space consists of HHH, HHT, and then HTT, HTH, and then TTH, THH, THT, and the last is TTT. And then I have the event A here, which consists of H, 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 T, H, T, T, and H, T, H. And then I have the other event B, which consists of H, H, T, H, T, H, T, H, H. So what is the probability of the union between A and B? Can anyone answer it? Anyone? I have the sample space like this, and then I have another events, A and B, which consists of these elements. And the question is, what is the probability of the union between A and B? So first we have to calculate the probability of A. What is the probability of A?
4
4
over
over
8.
8.
Okay, 4 over 8. Yeah. Then what is the probability of B?
3
3
over 8.
3 over 8.
Yes, 3 over 8. And the next question is, are there any intersection between A and B? Are there any intersection between A and B?
Yes.
Yes. So what is the intersection?
HHT,
Yes.
HTH.
HHT and HTH. Okay. So what is the probability of the intersection between A and B?
2 over 8.
Yeah, 2 over 8. So we can calculate the probability of the union between A and B as the summation between probability of A and probability of B, and then minus the probability of the intersection between A and B. So we have the value here is 4 over 8 plus 3 over 8 and then minus 2 over 8. So we have here is 5 over 8. So this is how we calculate the probability of the union between A and B for the general case. So this general case is assuming that we have intersection between events. Okay. Yeah, so the rule in the equation number 6, we have equation number 6 here. Yeah, can be generalized or can be extended into 3 or more events. For example, for 3 events, that is, we can calculate the probability of the union between A, B, and C, and we can calculate it by using this equation. So how come this one being the equal value with the probability of the union between A, B, and C? So we will just do a little proving here. Okay, yeah, so this is the proof. So we can rewrite the probability of the union between A, B, and C here. Yeah, we will rewrite it as the probability of the union between A and B. And then this result, we also unify it with C. Okay, so just assume that the first variable here, we can rewrite it as the other events, call it as D. So we have here probability of union between D and C is, we will use the equation equation 6 before. So this is the summation between probability of D and then probability of C minus the intersection between D and C. Yeah, so D here is union between A and B. So this is probability of D plus probability of C minus probability of the intersection between D and C. Yeah, because the union between A and B is called D. So we have the equation like this. So then we will derive again the probability of the union between A and B using the equation 6. So we have here probability of A plus probability of B and then minus probability of the intersection between A and B. And then plus the probability of C here. And then we have that the union between A and B and we intersect it with C, it will be the intersection between A and C, and then we unify it with the intersection between B and C. So this is the rule of the distributional in set theory. I think you have obtained it in the senior high school. So we extend the probability of the intersection between D and C here to become like this. Okay, so we just continue to the derivation of this one because this is the union, so we can say again that the intersection between A and C will be X and the intersection between B and C we call it as Y. So here we have the probability of the union between X and Y. So this is equal to the probability of X plus the probability of Y minus the probability of the intersection between X and Y. So if we extend these equations, we have the probability of X here plus the probability of Y here minus probability of the intersection between X and Y. And then again, we will extend the equation. So we have here probability of A plus probability of B plus probability of C. Yeah, we just make it to the front. Here, the probability of C. And then minus the probability of the intersection between A and B. And then minus the probability of intersection between A and C. Minus probability of intersection between the intersection between X and Y here. Okay, so this will come to the proof of this equation. Yeah, I think you can read again next, but we will jump to our example. So I think it's a little bit more challenging. Yeah, so I have the question here. Consider a pack of 52 playing cards. A card is selected randomly. So the question is, what is the probability that the card is either a heart or a 7? So do you know this pack of playing cards? So do you know the element of this 52 playing cards? So we have the notes here. The 52 playing cards consist of 13 ranks in each of 4 suits. So we have 4 suits, clubs, and then diamonds, hearts, and spades. And then each of these suits consists of ace, consists of ace and then the card number 1 until 9. And then the additional king, queen, and jack. And it is the same for all other suits. So we have, for each suite, we have 13 cards. Okay, so the question is, what is the probability that the card is either a heart? So the question is, what is the probability that the card is either a heart or 7? So this is the question. So using the additional rule of probability, we will have to sum the probability of heart and the probability of 7 minus the probability of the intersection between heart and 7 card. So my first question is, what is the probability of heart? Anyone? What is the probability of heart? Hello, anyone?
Yes, yes, madam,
13
can you
over
repeat it?
Oh, okay. So suppose that we have 52 playing cards, which consists of 13 cards for each suit. So we have 4 suit, consists of clubs, and then diamonds, and then heart and spades, and then each of the suits consists of 13 cards. What is 13 card? These 13 cards consist of ace, and then we have 1, 2, 3 until 9 card number, and then we have king, queen, and jack for each suit. So we have 13 cards in each suit. We have 13 cards in clubs, we have 13 cards with diamonds graph, and then we have 13 cards with hearts, and we have 13 cards with spades. So the question is, what is if I select one card randomly, so what is the probability that this card is either heart or a 7? So to calculate this probability, we have to calculate the probability of the heart, and then the probability of the card number 7, and then the probability of the intersection between heart and card number 7. So my question is, what is the probability of heart from this element of cards? What is the probability of heart? We have 13 clubs, we have 13 diamonds, we have 13 hearts, and we have 13 spades. So what is the probability of heart?
13 over 52.
Okay, 13 over 52. Yes, right. And then the second question is, what is the probability of the card number 7?
4 over 52.
Okay, 4 over 52. Yeah, because we have 7 here, we have 7 here, 7 here, and 7 here. We have 7 in each suit. So in clubs we have 7, in diamonds we have 7, in hearts we have 7, and in spades we have 7. So we have 4 over 52. Okay, and then the last one is, what is the probability of the intersection between heart and the card number 7? Anyone?
One over 52.
Okay, yes, right. 1 over 52. Yeah, because we just have one card number 7, which is heart. Yeah, so the answer for this question is 13 over 52 plus 4 over 52 minus 1 over 52. Yeah, so we have here 16 over 52.
16 over 52.
Yeah, right. Okay, thank you. Thank you, everyone. Okay, so I have another question. Okay, imagine that we have some athletes in a room consists of 5 men with a height of 170 centimeters and over, and then 4 men with a height of under 170 centimeters, and then 6 women with a height of 170 centimeters and over, and then 3 women with a height of under 170 centimeters. So we can define the following events. Suppose that we have 4 event A, B, C, and D. A represent the athlete with a height of 170 centimeters and over, and then B represent the athlete with a height of under 170 centimeters, and then C represent the athlete is male, and then D represent the athlete is female. So the first question is, what is the probability of the union between B and D? And the second question is, what is the probability between the complement of what is the probability of the intersection between the complement of A and the complement of C? So for the first question, the probability of the union between B and D, we can calculate it by summing the probability of B plus probability of D minus the probability of the intersection between B and D. So again, we have to calculate the probability of B, probability of D, and then probability of the intersection between B and D. So I want you to answer, what is the probability of B? B is the event represent the athlete with a height of under 170 centimeters. So what is the probability of B?
7/18.
Sorry?
7/18.
7? Sorry, can you repeat?
Probability B.
Yeah, probability B.
7/18.
7/18. So let's see, we have 5 men with the head of sorry, what we want to calculate is that one under 170 centimeters. So we have 4 men with head of under 170 centimeters and 3 women with a head of under 170 centimeters. Okay, so we have 7 over all of these athletes. We have 5 and 4, 6 and 3, so we have 18. Yeah, so right, the answer is 7/18. Okay, thank you. So the next is, what is the probability of D? D is that the athlete is female.
9/18.
Okay, 9/18. Yes, right, thank you. And then the last one, what is the probability of the intersection between B and D? So what is the intersection between event B and D is that the athlete is woman and under 170 centimeters. So what is the probability of the intersection between B and D?
3/18.
Yeah, right, thank you. 3/18. So we have the answer here, probability of the union between B and D equal to 7/18 plus 9/18 and then minus 3/18. So we have 13/18 here. Okay, thank you. Okay, so the second question. What is the probability of the intersection between the complement of A and the complement of C? What is complement of A? We have to know first that A is the athlete with a height of 170 centimeters and over. So what is the complement of C? Sorry, what is the complement of A? Hello? Yeah.
The complementer of A, right?
Sorry? Yeah, complement of A. What is the complement of A?
7/18.
7.
I asked first what is the complement. We don't discuss about the probability. What is the complement first? I want to know what is the complement of A, not the probability of the complement of A, but what is the complement of A?
7.
10/18.
For men to women.
For man to woman? Other answer, maybe? A is the athlete with a height of 170 centimeters and over. What is the complement of this one? Anyone? Yeah, Afif?
Not for men and to women, right? Because it said it's not 170 cm and above.
Yeah, so complement of A is all of the athlete with a height of under 170
Under
centimeters.
170.
Yeah, so the complement of C is equal to D, right?
Yes.
Yes, okay. And then what is the complement of C? C is the athlete, represent the athlete is male. So what is the complement of C?
Uh, 6 and 3.
Sorry? Your voice is not clear.
6 women with 170 cm and over, and 3 women with under 170.
Okay, so we can also say that the complement of C is all the athlete that female. Okay?
Yeah.
Yeah, so we can also say that the complement of C is equal to D. So the probability of the intersection between the complement of A and the complement of C is equal to the probability of the intersection between B and D. Yeah, so what is the answer here? The intersection between B and D. So the intersection between B and D, like this one, right? Yeah, so we have 3/18 here. Okay, yeah. So until this section, any question, you can raise hand if you have any question. Before I continue to the next part of this class. Any question?
No, ma'am.
No? Okay. If there's no question, I will continue to the next section, which is about the conditional probability. Okay, so first, before I explain about the formal definition of the conditional probability, I will give you one illustration here. So suppose that we have a box contains of 3 black balls and 4 white balls here. So you can imagine, just imagine that we have a box and then we have 3 black balls and then 4 white balls. And then 2 balls are drawn randomly without replacement. So I will take the first ball randomly and then I will again take the second ball. So first, consider we have two events here. The first event, call it as A. The event A represent the first ball drawn is black. So imagine that I take a black ball. Yeah, so this is for the first event. And then for the second event, or we can say it as event B, represent the second ball drawn is white. So imagine that the second ball I have taken is white. And then we know that the probability of A here, the probability of A is equal to, what is the probability of A?
3/7.
3/7.
Yeah. Right, 3/7. Okay. So, what is the probability of B?
4/7.
4/7.
4/7. But we define that B is the second ball drawn is white. So this is the second drawing. Yeah.
4/6.
Yeah. 4/6.
4/6.
Yeah, you right. Okay, you are right. So this is not as simple as we calculate the probability of A, because we have two process. The first process is we take one ball, and then the second process, without without the replacement of this first ball, then we take again another ball. So from the first process, there is one ball which is missing from this box. So we have 6 balls left, which consists of 2 black balls and then 4 white balls. So if the question is what is the probability that the second ball drawn is white, so the probability is 4/6. Yeah, because this is the second ball, not the first ball. If please, can you different between this one? So I have C, the first ball drawn is white. If I have this event, so what is the probability of C?
4/7.
Yes, right. 4/7. So can you see the difference between B and C? Yeah, I think you can see the difference between the probability of B and C. The probability of B is then when we calculate the probability for the second ball. But for the C, event C, we calculate the probability of the first ball. So this is quite different. So this is the basic concept of the conditional probability. We can see that in this explanation, if the first ball drawn is black, so in the box consequently contains of 2 black balls and 4 white balls. So in this case, the probability of B is equal to 4/6. However, if the first ball drawn is white, so we can see that if the first ball drawn is white, so we have 3 black balls left and then 3 white balls left. So we have the probability of B is equal to 3/6 if the first ball drawn is white. So the first process give an effect to the second process. So it is called the conditional probability. Yeah. If we calculate the probability of an event that is being impacted from the first event or from the previous event, so it is called conditional probability. Yes, so yeah, so I will jump to the here to the formal definition of the conditional probability. So if we want to calculate the conditional probability, it is denoted by probability of B given that A occurred. From the example, we know that A is the first process and B is the second process. So if we want to calculate the probability of the second process given by the previous process, so we can calculate it by dividing the probability of the intersection between A and B divided by the probability of the previous process or previous events. Okay, so this is the formal definition of the conditional probability. And I have another example for the conditional probability. So imagine that there's a box contains of 6 50-watt LED lamps and 10 100-watt LED lamps. So we have 6 for 50 watt and then we have 10 for 100 watt. And then the lamps are all unmarked, so we don't know which one is 50 watt and which one is 100 watt, and are of the same physical size. So we cannot differentiate between the lamp which is 50 watt and which is 100 watt. And then for the first point, one lamp is picked at a random from the box. And then we have to determine the probability that it is a 50-watt LED lamp for the first question. And for the second question is what is the probability that it is a 100-watt LED lamp. So for the first one, the probability of that this is 50-watt LED lamps is equal to, we just picked one lamp without any process, without any picking again. So what is the probability that the randomly picked lamp is the 50-watt LED lamp?
6/16.
Yeah, right. 6/16. Okay. So the second question is, what is the probability that it is 100-watt LED lamp?
10/16.
Okay, 10/16. It is the rest. Okay, so for the first problem, we have no further process. And then we jump to the next problem. Okay, for the second problem, at the start, 2 lamps are selected from the box. Like the example before, so I select one lamp first, and then I select another lamp for the second process. So determine the probability that both are 50-watt LED lamps. What is the probability that both are 50-watt LED lamps? Anyone can answer? Okay. How can we answer this question? If the question is what is the probability that both are 50-watt lamps, so we have to maintain in our mind that if both are 50-watt LED lamps, so the first process or the first selection will be 50-watt LED lamps, and then accompanied by the second process, which is also 50-watt LED lamps. So we have here the probability that both 50 watt is equal to How come? Anyone can answer? I will give you opportunity to try first before we discuss about the answer. How do we calculate this one? Okay, first, let us remind about the formal definition of the conditional probability. Probability of B given A is equal to the probability of the intersection between A and B divided by the probability of A. Yes, Dr. Ida? Why you raise your hand? Any something do you want to tell? Yeah.
You have 15 minutes left.
Oh yeah. Okay. Yeah. Okay, doctor. Okay. Before I continue a little bit more, I have a quiz for the student, which can be participated by using the quizzes. Is it includes in this 15 minutes or after that? After that?
After this, yes.
Oh yeah. Okay. Thank you. So I will continue a little bit more. Yeah. Okay, so we have to remind that we have the formal definition of the conditional probability like this, or it is equivalent. This is equivalent to that we will calculate the probability of the intersection between A and B is equal to the multiplication between the probability of the conditional probability of B given by A multiply with the probability of A. So if the question is what is the probability that both are 50-watt LED lamps, it is equal to the first process is first process is 50-watt LED, and the second process is also 50-watt LED lamp. So we can calculate the probability of this one by multiplying that the first process is that we select, Okay, so for the first process, we select the 50-watt LED lamp, and then the second process, we also select the 50-watt LED lamp. This is for the first process. I can say it as P1, and then this is the second process if given that the first process is also 50-watt LED lamp. So the probability of 50-watt LED lamp will be selected is equal to the 6/16. And then because one of these lamps is selected, so we have five for the 50-watt LED lamps which live in the box. So here we have 5/15. Okay, because we have taken one lamps before. So the rest of the lamps in the box contain of 15 lamps, which consists of 5 50-watt LED lamps and 10 100-watt LED lamps. So this is the answer of the first question. Okay. So the second one, what is the probability that the first is 50-watt and the second is 100-watt? So how can we calculate this problem? Okay, we can see here the first is 50 and the second is 100. So what we have to calculate is the probability of the intersection between the 50 watt and is the intersection with 100 watt. And again, we will use this calculation. So in the first process, we will take the 50 watt, and then the second process we take the 100 watt, given that the first process is the 50 watt LED lamp. So the probability of that the taken lamp is the 50 watt LED lamp is 6/16, and then the second process after the first process that taken lamp is the 50 watt, so we have here 10/15. So this is the answer of the second question. Okay, so the last question, I think also the last discussion of this class. What is the probability that both are 100 watt LED lamps? So it is the same. How can we calculate this probability? Anyone? Just for the last question, I want to anyone answer this question. Probability that both are 100 watt. So it is equal to anyone? Hello? Or we can say that if both are 100 watts, so in the first process, we take 100 watt. Yeah, and then the second process, we also take 100 watt, given that the first process is 100 watt. So what is the probability that the taken lamp in the first process is 100 watt? Anyone can answer?
10/16.
Yeah, 10/16. So what is the probability, the conditional probability that the second lamp is 100 watt, given that the first lamp is also 100 watt?
9/15.
Yes, right, 9/15. So this is the basic concept of the conditional probability. I think because the time is out, so you can continue to read by yourself. My slides I will share to Dr. Ida then, so you can also read in your own time. And I think maybe it's enough from me. Before I close my discussion today, I apologize that if any discussion is not clear from me. Thank you very much, Dr. Ida, and I give the time again to Dr. Ida.
Okay, thank you so much, Dr. Atina, for the session. I do believe the session, the duration of session is quite short to cover everything about the topic. But I guess it's a fruitful discussion. I guess the student learn a lot from you. Alhamdulillah. So here today, do you have any question for the student? Do you have any more question to Dr. Atina? Okay, I guess there are no more question. So on behalf of the organizer, I would like to thank Dr. Atina for your time and also effort and to make this program is a successful webinar, inshallah. I do hope we have some more collaboration in future, and more working together. And so I do believe, and I hope we still can keep in touch for our next project, inshallah. So
Amin, inshallah.
as today, so thank you so much for coming to our session. To the students, please fill up the attendance on your WhatsApp group or your Telegram, depending on your preference. And also, that's all for today. I guess thank you so much for the time. So Alhamdulillah.
Thank
So
you.
maybe we can have some group photo session.
Oh yeah. I have to stop presenting.
Sure.
Yeah. Okay.
Okay. Can the student open the camera?
Hi, Dr. Atina.
Hello, Dr. Ahdika.
Thank you so much for your
You are most
presentation.
welcome, Dr. Ahdika.
Hope to see you again
Yes.
anytime.
Yeah, I hope so. We can make any collaboration in the future.
Inshallah.
For sure.
Inshallah, yeah.
Okay.
Okay. All right. Okay. So, okay. Faris Chomel. Okay. 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 One. And Faris Chomel. Where's Faris Chomel? Okay. 1, 2, 3. Okay, another one. 1, 2, 3. Okay then. Thank you so much. Thank you so much for the participation. Alhamdulillah. We hope to see you again, inshallah. Bye-bye.
Yeah, I hope so. Thank you very much, Dr. Ida,
Inshallah.
Dr. Afida,
Okay.
and all of the staff of UiTM.
Yeah, inshallah.
Okay.
Dr. Tina,
Yeah?
do you want to share the slide with us? Or?
Yeah, of course. I will send it to Dr. Afida
Sure,
after
sure,
this
sure.
class.
Thank you so much.
Yeah.
Thank